13.6, the binomial theorem. So an expression of the form a plus b is considered a binomial because it has two terms. And what we can do is take this binomial and raise it to any power. And we've seen this when we raise it to a square, we get a perfect square trinomial. When we raise it to the third power, we get that special cube. So when we're expanding it to really any power, it's going to follow a very special pattern. And to find that pattern, really we can raise it to the first, the second, the third, the fourth, and so on. So if we raise it, well, actually we could even start at 0. We know anything to the 0 power is 1. And then a plus b to the first power is obviously just a plus b. When we square, we're going to get that's a squared plus 2ab plus b squared. Okay. And then we can just continue this pattern. A plus b cubed, that's going to give us, let's see, a plus b times a plus b times a plus b. We know we have a squared plus 2ab plus b squared, and then we'll multiply again. And we'll start to see a pattern when we go through all of this. A squared b, let's see. Oh, I missed it. No, hang on. A cubed, a squared b, then 2, nope, that's right so far. And then plus 2ab squared plus b squared a plus b cubed. Okay. And we can combine a little bit of this. So that's a cubed plus 3a squared b plus 3ab squared plus b cubed. All right, so that's for our third one. And we could keep going, but obviously it's going to get very, very long. What's interesting to note, though, is the coefficients. So we know anything to the 0 power is 1. These both have coefficients of 1. These have 1, 2, 1, 1, 2, 1. These have 1, 3, 3, 1, 1, 3, 3, 1. And we notice that it's starting to form a pattern. So this is actually going to give me a to the 4th power plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the 4th power. And we can start to use this special pattern. Now this actually has a special name in and of itself. It forms a triangular pattern. We call this Pascal's triangle. Now Pascal was a mathematician who played with numbers, and this was a special pattern that he found. And what he did to create this pattern was he started with 1, and as you can kind of tell, it follows 1 along down the sides. All right. Now, to get the rest of the numbers, what he did was add. So 1 plus 1 makes 2. And 1 plus 2 makes 3. And 2 plus 1 also makes 3. And really, to get the sides, you're adding 1 and nothing. All right? So to get 4, it's 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and so on. So if I wanted the next row, I'd have a 1 on the outside. 1 plus 5 is 6, 5 plus 10 is 15, 10 and 10 is 20, 15 and 6, and that 1 would be on the outside. So we would continue this pattern down as many times as we need, and actually, we just answered the next question. So a plus b to the 6th power, it's actually going to come from this pattern here. We have 1, 6, 15, 20, 15, 6, and 1. And what happens when we do this is we start with the first letter and raise it to this power. So that's a to the 6th power plus. Now what we're going to do is drop that down a power, so it's a to the 5th, and pick up the next one. So that's b to the 1st. So technically this was a b to the 0 power. All right. Now dropping down again, that's a to the 4th. Now that'll become b squared. Drop down the a again, bring up the b. Drop down the a, bring up the b. Drop down the a, bring up the b, and drop down the a to nothing and bring up the b to the power you are raising it to. And that's our special pattern that we use in order to find Pascal's, or use Pascal's triangle to help us out here. All right. So, and again, that's because we are really starting with the first letter. That's going to start at this number and count down, whereas this is going to start at 0 and count up. All right, so technically this had an a to the 0 with it. The Pascal's triangle is useful for so many different things. It's not just for binomials, but that's what we're going to use this chapter for. You'll start to find all sorts of crazy patterns in here. We see if we go down this row, this, I guess, diagonal, 1, 2, 3, 4, 5. Okay, we're counting by ones. But if we go down different patterns, we can start to find multiples. We can start to find triangular numbers. We can find all sorts of crazy things going on. If we add them up, you'll start to see we even get special patterns with their sums. So 1 and 1 makes 2, 1, 2, and 3 make 4, 1, 3, 3, and 1, that's going to be 8. And we actually can start to get our second power, right? 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and so on. All right, so Pascal's triangle is useful for all sorts of things, but it's not always practical for large numbers. I mean, if I asked you what a plus b to the 15th power is, are you going to sit here and write out all of Pascal's triangle? You could, but it's not the best solution here. So we have an option. We have another option. So in other words, to find the 100th row, we're going to need to use the 99 rows before it, especially if we're using Pascal's triangle. So the method we're going to use is, the method we use for finding the successive rows is what we call recursive, and that's what it means. We would need to know every row that came before it, so this just isn't practical. So we have a special formula instead. The product of the first n natural numbers is denoted by n, and we see that exclamation point there. It means n factorial. So we read the exclamation mark as the word factorial. So if I have the number 5 factorial, what that means is 5 times 4 times 3 times 2 times 1. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. So we're going to start at whatever the number is before the exclamation point and use all of the integers down to 1 to multiply. So 5 factorial is going to give us 120. And that's just by multiplying all of those numbers together. Now, we do define 0 factorial as 1. I know that seems strange. We had to give it something there. It's just a special notation. All right, so let's let n and r both be non-negative integers, and let's say that r is less than or equal to n. So what we say is the binomial coefficient is denoted by this special form. We see these parentheses and that n on top and the r on the bottom. Okay. And we have a special formula for this. We'll get into probability soon. This actually has a lot to do with probability. That's actually going to be in chapter 14 coming up. But we can find the binomial coefficient by using this formula. Okay. So we're going to practice using this formula, n factorial over r factorial times n minus r factorial. We're going to start using the special formula just to practice it. Okay. So n is on top and r is on the bottom, and remember, we are just plugging in. So that's going to give us 9 factorial over 4 factorial times 9 minus 4 factorial. All right, well, 9 minus 4 is 5. We can start there. And we have a few ways of doing this, but let's write out real quick. We won't always have to do this, but let's write out what it means. Okay? So that really means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is, actually, let me switch colors. 4 factorial is going to give us 4 times 3 times 2 times 1. And then 5 factorial is going to give us 5 times 4 times 3 times 2 times 1. So if you're doing this by hand without a calculator, you can start to see where you can cancel some things out. Since it's multiplication, think like how we cancel with variables. 5, 4, 3, 2, 1 can cancel with 5, 4, 3, 2, 1. So that'll help us out a little bit. And then if you want to look for more things to cancel, you can. But it's we still have to do the multiplication here. So 9 times 8 times 7 times 6 over 4 times 3 times 2 times 1. That's going to give us 126. All right. So let's try it for the next one. That's going to give us 100 factorial over 3 factorial times 100 minus 3 factorial. All right, so we have 100 factorial over 3 factorial times 97 factorial. And this is where that crossing out can really help us. Now, I'm not going to write out every number here, but we have 100 times 99 times 98 times 97, 96, 95, all the way down to 1. All right, then we have 3 times 2 times 1, and then we have 97 times all the way down to 1. Well, that 97 all the way down to 1 can cancel in the top and the bottom. So really, I just have 100 times 99 times 98 over 3 times 2 times 1. And that is going to give us still a rather large number. That's 161,700. Okay. One more, we have 100 factorial over 97 factorial times 100 minus 97 factorial. All right, that's going to give us, again, 100 times 99 times 98 times 97 all the way down to 1. And then here we have 97 all the way down to 1. And that's going to give us 3 factorial. So we have 3 times 2 times 1. And we can cross out that 97 all the way down to 1. And that actually also gives us 161,700. Okay. All right, so although the binomial coefficient is defined in terms of a fraction, it'll always result in a natural number, in a countable number. So we're not going to get anything negative. We're not going to get a decimal here. Okay. All right, so to see that connection between the binomial coefficients and the binomial expansion of a plus b to whatever power, let me show you what happens when we calculate a few different things. Well, we'll get there. So if we did 5, 0, right, 5 over 0 here, that's going to give us 5 factorial over 0 factorial times 5 minus 0 factorial. That's going to work out to be 1. If I do 5 over 1, whoops, not over 1, there we go, that'll give us 5 factorial. We have 1 factorial, 5 minus 1 factorial. That'll give us, let's see, 5. And if we keep doing this, 5, 2 is going to give us 10. 5, 3 is also going to give us 10. 5, 4, whoops, is going to give us 5, and 5 out of 5 is going to give us 1. When I work these all out, we're going to start to see a pattern, and that pattern is really in Pascal's triangle. Okay. So we're also going to notice that when n minus r is the same as r, we're going to get the same answer. Okay. So when the difference between n and that other number is the same as that other number, then it doesn't really make a difference. Just like we saw up here, 103, the difference, 100 minus 3 equals 97. That's why these are the same, because 97 is the difference between these two numbers. Okay? You're going to end up with the same thing. So that's why we're getting this 10 and the 10 here. 5 minus 2 is 3. 5 minus 1 is 4, so that's why we're getting 5 and 5. 5 minus 0 is 5, so that's why we're getting 1 and 1. So Pascal's triangle really can be thought of similarly to this. If this we consider to be row 0, here we have row 1. We're going to put a 1 in the top part and then just start with 0 each time. All right, this is row 2, 2, 0, 2, 1, 2, 2. Row 3, row 4, 5, and so on.